Okay, so we have been talking about conduction problems that were one-dimensional in steady state, and we went through problems that were truly one-dimensional. We went through problems that could be approximated as being one-dimensional, so extended surface problems. And we also have solved these problems analytically and numerically. So today what we're going to do is move on to problems that are two-dimensional, right? And we're going to focus on solving them analytically, and the tool that we use to solve these kind of problems analytically is separation of variables, right? So that'll be the topic of the next few lectures. Separation of variables is, kind of the go-to tool to solve partial differential equations. It's obviously going to be useful to you even outside of heat transfer, but this is a really nice place to learn it if you've never seen it before. So I think the best way to learn this approach is in the context of a specific problem. So we're going to do this problem that I've drawn here. This is a two-dimensional conduction problem, and we will go through it very slowly, sort of delineating the steps and why we're taking the steps versus just sort of taking steps and at the end we get the right answer, but sometimes it's hard to know how do we see all the way to the end. So hopefully if you follow these steps, you'll be able to take this approach and apply it to other problems that aren't exactly like this one. All right, so separation of variables is a two-dimensional it's an analytical technique for solving partial differential equations. Here is our particular problem that we're going to solve. So this is a rectangular plate. The width is W and the height is H. It's thin in the Z direction, right? So this is X and Y. This is looking down on it from the Z direction. If you look at it, I guess this would be in the Y direction. You'll see that this is a thin plate with thickness B. What else? So the boundary conditions on the plate are that this edge here at x equals 0 is held at temperature 0, which is obviously a little bit silly, right? There is no temperature 0. So really you ought to think about that as some kind of a reference temperature, right? And every other temperature is defined relative to that reference temperature. So here's our 0 reference temperature. This upper edge is held at a different temperature, TH, right? So two-dimensional problem. We definitely have heat flowing in the X direction and the Y direction, because if I'm going to start here as a piece of energy, the only way I have to get out is over here, so I have to move sort of both down in the Y direction and across in the X direction, and that motion is going to give me temperature gradients in the X and the Y direction. Right? This edge here at X equals W is insulated. This edge here at Y equals 0 is also insulated, so there's no approximation I'm going to make that's going to get rid of the two-dimensionality of this problem. Right? This is clearly a two-dimensional problem. The top and the bottom surfaces here at, I guess, Z equals 0 and Z equals B are both insulated, so there are no temperature gradients in the Z direction. All right, so that's our problem. We need to, before we can solve it, come up with the differential equation that we're going to try to solve, right? So we go through the same steps to derive the differential equation. They get a little bit more complicated now because our temperature is two-dimensional, right? But the steps in terms of literally exactly what you're going to do are the same. So if you remember, the first step that we do in deriving a differential equation is we define a differentially small control volume, and that differentially small control volume needs to be differentially small in the directions that the temperature is varying. So in this particular problem, temperature is varying in X, it better be differentially small in X. Temperature is varying in Y, better be differentially small in Y. Temperature is not varying in Z, so it can extend all the way across the plate in Z. And that's what I've done here, right? This is my differentially small control volume. It's dx, dy, but then if you look down here, it extends all the way across the plate in the Z direction. Eventually, we're going to shrink dx and dy both to 0 for this particular problem. So that's step one. Step two is do a first law balance on your differentially small control volume. So if I have temperature gradient in the y direction, I'm going to have heat flowing in the y direction. So I guess, sorry, that would be this direction. If I have temperature gradient in the x direction, I'm going to have heat flowing in the x direction. So what that means to me practically is I'm going to have heat flow across this boundary and across this boundary, and heat flow across this boundary and across this boundary. Right, so I will have q dot in the x direction at location x, that's crossing the left side of this differential control volume. I have q dot in the x direction at location x plus dx, so that's what's leaving over here. Q dot in the y direction at location y is coming through the bottom, and q dot in the y direction at location y plus dy is leaving the top here. Right, those are my energy transfer terms. I don't have any stored or anything else going on for this particular problem. I'm still at a steady state. What's the next thing that we do? So step 3 is you write down your energy balance. I have in equals out, and then you expand the x plus dx and you expand the y plus dy terms and take the limit as dx and dy go to 0. And that's all I've done here. Q dot x at x plus dx becomes q dot x at location x plus dq dot dx times dx, right? And the same thing here for q dot y at location y plus dy, right? I've taken advantage of the fact that dy is shrinking to 0 in order to express this in terms of a derivative. Right? One thing that you'll see right away is instead of having ordinary differentials, I start to have partial differentials popping in here, because q dot in the x direction, this q dot x term is not a function just of x. It's going to be a function of x and y, just like temperature is going to be a function of x and y. So I'm taking the partial derivative of that with respect to x. Okay, so I can cross out, I can cancel out q dot x at location x from both sides. I can cancel out q dot y at location y from both sides, and I'm left with this this partial differential equation, right? So just like always, I end up with a differential equation that's written in terms of energy, because energy is fundamentally the thing I'm trying to balance, right? This is basically saying that the reason that q dot x is changing as you move in the x direction is because q dot y might be changing as you move in the y direction, right? This heat might be turning a corner, basically, is what this is saying. If I want to make this a a differential equation that's written in terms of temperature, then I need to substitute in rate equations, right? Same thing we've done multiple times, right? This is our step 4. So these are both conduction terms, so my rate equation twice is going to be Fourier's law. I have q dot x, so q dot in the x direction is going to be minus k times a times dt dx, right? So minus k times the area in the x direction is dy times b into the page, so b times dy times dt dx. Same thing over here, q dot y is minus k times the area in the y direction, so the area for this heat flow is dx times b, so that's what I got here, times dt dy. So I substitute this into here, I substitute this into here, I'm left with this. I'm going to divide through by everything that's constant in one of these two derivatives. So let's see, minus k is constant, b is constant, and then I have dx and dy. I happen to have exactly the same things over here. So I'm left with this differential equation here. This is sometimes called Laplace's equation, right? This is the partial differential equation that you often get when you're trying to solve conduction problems. I need some boundary conditions. When we had a one-dimensional problem, my boundary conditions were at the extent of my computational domain, which was at basically 2 points, right? So for maybe x equals 0 and x equals w. Here I have a two-dimensional problem, so the boundary conditions are still at the extent of my computational domain, but these now become lines, right? So I need a boundary condition at x equals 0, but for all y values, right? So that's along this line, and that is the temperature is equal to 0. I need a boundary condition at y equals h, but for all x values, right? So that is temperature equal th. I need a boundary condition over here, right? And that is that the rate of heat transfer due to conduction has to be equal 0, right? The rate of heat transfer in the x direction over here has to be equal to 0 because it's adiabatic. So that's going to, by Fourier's law, tell me that the gradient of temperature with respect to x at x equal w has to be 0, right? That's just saying it's got to have a flat temperature distribution at this wall here, because if it didn't, then I would be pumping energy into this wall, and there's no place for that energy to go. And the same thing down here. dt dy at y equals 0 needs to be equal to 0. So these are my boundary conditions, and this is my partial differential equation, right? So, we can come up with different techniques to solve these different problems, but the derivation of the problem themselves is always going to be on you, right? You have to be able to derive the differential equation in the boundary conditions that you want to solve, and then we can follow through some steps and try to come up with a solution, right? So we'll try to solve this partial differential equation using separation of variables, and there are some very prescribed steps that take a little bit of getting used to, right? But once you've done it a couple times, you really start to get the hang of it, right? And that's actually pretty nice, because like I said, you can take it from this domain or this context and you can apply it to different other contexts and get a solution there as well. So here's step one for using separation of variables, right? For this math problem. At this point, it's just a math problem. The first step is to check that your problem actually meets all the requirements that would allow you to use separation of variables, right? It's not true that separation of variables can be used to solve any partial differential equation, right? It's only going to be useful for partial differential equations that meet a certain set of requirements, and those are listed here. And actually, if it doesn't meet this set of requirements, there's all these different techniques and tricks and whatnot that you can use to try to break it into simpler problems that do meet these requirements. And we'll talk about superposition when we're all done in a couple of lectures. But before you just sort of dive into separation of variables, you better be sure that these things are true, right? So the first thing is that your partial differential equation and all of your boundary conditions have to be linear. So linear, again, means that you can't have temperature multiplied by temperature and its derivatives, right? Temperatures all have to sort of stand alone. So that's what we have here, right? We don't have any temperature to the fourth power or dt dx squared or anything like that, right? Everything is linear. All the temperature and temperature derivative terms are sort of standing alone. The computational domain must be simple. So what does that mean? That means that the boundaries here have to fall on lines of constant coordinate directions, right? So in other words, this boundary is along the line of y equals 0. This boundary is along the line of x equals 0, and so on. It has to be square, basically, or at least rectangular. And certainly that's true here, right? All of our boundaries are on lines of constant coordinate directions. The PDE must be homogeneous. So again, what homogeneous means is that if you find a solution to the problem, you can multiply that solution by any constant, and it remains a solution, right? And practically what that means is if you put all the temperature stuff on one side, the other side is 0, right? Because if I put all the temperature stuff over here, and then I multiply my solution t by a constant, that constant I can cancel from both sides. And I can't do that unless the right-hand side is 0. So this PDE is certainly homogeneous, right? There's nothing over here that would wreck that. And then this is actually really important, this last one, and that is that both of the boundary conditions in one of the two directions, not both directions, but one of the two directions has to be homogeneous. So either the two boundary conditions in x or the two boundary conditions in y have to be homogeneous, right? So let's look at the two boundary conditions in x, right? So here I have a boundary condition at x equals 0, and here I have a boundary condition at x equals w. Both of these two boundary conditions are homogeneous, right? These are, if I find a solution to the problem and I multiply that solution by a constant, it's going to remain a solution because the constant will just pop out. I can cancel it through, and I still have a constant, right? The right-hand side of these two equations are 0. In the y direction, this boundary condition is also homogeneous, right? dt dy at y equals 0 is equal to 0, but this last boundary condition is not, right? So y does not have two boundary conditions that are not homogeneous. It only has one. And in fact, I could continue with separation of variables even if both of these were not homogeneous. All I require is that one of my two directions have homogeneous boundary conditions. And in this case, that direction is x. My x direction is my homogeneous boundary condition, my homogeneous direction. And I have to remember that because that actually dictates some choices that I make further down the line, right? So in this particular problem, the x direction is my homogeneous direction. I will point out that if you had a problem where everything was homogeneous, it would be a really boring problem, because if everything is homogeneous, then the answer is 0, right? You can see that here. This is equal to 0. These three boundary conditions are homogeneous. They're all equal to 0. If this last boundary condition was also homogeneous, so the temperature at y equals h was equal to 0, I can tell you the solution. It's that the temperature everywhere is just 0, right? And so it's the non-homogeneous terms in your problem that are actually causing the interesting behavior, right? So in this case, this is the only term that's causing something to happen.